Hello, and welcome to this lesson on integration by substitution. When we were studying derivatives, we saw the chain rule. The chain rule was used whenever a function, an algebraic expression, was inside another function, a grouping symbol. For example, if we have the function f of x is equal to the sine of 3x. The 3x is inside of the sine function. So taking its derivative using the chain rule, we do the derivative of the container, so the derivative of sine gives us cosine, times the derivative of the inside, the derivative of 3x gives me a 3. So I get f prime is equal to 3 times the cosine of 3x. Integration by substitution, sometimes called U substitution, finds the derivative of problems where the chain rule was used to calculate the derivative. So let's take a look at using the U substitution, the integration by substitution. So first thing we want to do is let U equal to the algebraic expression that's inside the grouping symbol. Once we do that, we're going to take that equation and we're going to calculate the derivative of U. So we're going to calculate du using our differential notation. From that equation that we took the derivative, we are going to solve that one for dx, again assuming that our original variable was an x. So after we have built those equations, we are now going to substitute into our original integral. So every place where there's that algebraic expression exists, we replace that with a u. Every place where the dx exists, we replace that with the expression we built there. After substituting, if the variable x still remains, assuming that x was the original variable, we need to take the formula in step 1 and solve that for x, and then substitute again. And then at this point, we should now have something that has only the variable u. And it should have only du's, there should not be any dx's. Well, we're going to do our integration. After integration, we replace u with the algebraic expression that u was. Now please note that the above steps will help you with many problems. However, there are problems that use u substitution that do not follow these steps. Since u substitution can be used with any of the antiderivative rules and can be used many other ways, we are going to see several examples. Let's take a look at example 1. Find the indefinite integral. So we have the integral of the sine of 3x dx. So our solution, we let u equal to the algebra that's inside my grouping symbol. So u is equal to 3x. I want to calculate the derivative of this equation using our differential notation. So, derivative of u, that becomes a du, and the derivative of 3 times x, that gives me the coefficient of 3 times dx. So I have du is equal to 3 times dx. I want to solve this equation for dx. So that ends up giving me du is equal to, dx is equal to du over 3. So now we're going to substitute. So where the 3x was located, we replace that with a u. And where the dx was located, we're going to replace that with du over 3. So this is going to become the sine of u times du over 3. Well, this over 3, that's a 1/3. So I'm going to take that 1/3 coefficient and put that out in front. So I have 1/3 times the integral of the sine of u du. Alright, the antiderivative of sine is negative cosine. So I'm going to get negative 1/3 times the cosine of u plus my constant. And then my last step, where that u was located, I want to replace u with 3x. So this ends up giving me negative 1/3 times the cosine of 3x plus a constant. Let's take a look at example 2. Find the indefinite integral. So we have the integral of cosine of 3x dx. So here's our solution. U is equal to 3x, the stuff inside my grouping symbol. When I take the derivative, that gives me du is equal to 3 times dx. Solving this equation here for dx, that gives me dx is equal to du over 3. Now, we're in my integral where my 3x was located, I replace that with a u. And where my dx is located, I replace that with a du over 3. So I get the integral of the cosine of u times du over 3. Well, the over 3, that's a 1/3. So I'm going to pull that coefficient of 1/3 outside of my integral. That gives me 1/3 times the integral of the cosine of u du. Well, the antiderivative of cosine is sine, so I get 1/3 times the sine of u plus a constant. And then the last thing, where the u is located, I'm going to replace that with 3x. So my answer is going to be 1/3 times the sine of 3x plus a constant. Okay, let's take a look at example 3. Find the indefinite integral. So we have the integral of secant squared of 3x dx. Alright, my solution here, well, u is equal to 3x. That's the stuff that's inside my grouping. Du is equal to 3 times dx. That's the derivative of my u equation. Solving this equation for dx, that gives me dx is equal to du over 3. So inside my integral, where the 3x is located, I replace that with a u. Where the dx is located, I replace that with du over 3. Well, my over 3, again, that's a 1/3, so that becomes a coefficient outside my integral. And I get 1/3 times the integral of secant squared of u times du. The antiderivative of secant squared gives me a tangent, so I've got 1/3 tangent of u plus a constant. And now where the u is located, I'm going to replace that with 3x. So that gives me my answer, which is 1/3 times the tangent of 3x plus a constant. Let's take a look at another example here. So, example 4, find the indefinite integral of cosecant squared of 3x. Well, again, u is equal to 3x, the stuff inside my grouping symbol. Du is equal to 3 times dx. That gives me that dx is equal to du over 3. And now when I do my substitution, this gives me the antiderivative of cosecant squared of u times du over 3. Well, the over 3, that's going to become a 1/3 outside my integral. So I've got 1/3 times the integral of cosecant squared of u times du. The antiderivative of cosecant squared is negative cotangent. So I get negative 1/3 times cotangent of u plus a constant. And then lastly, I replace u with 3x. So I get negative 1/3 times the cotangent of 3x plus a constant. All right, example number 5. Find the indefinite integral. So I've got the indefinite integral of the secant of 3x times the tangent of 3x. So my solution here, I'm going to let u equal to 3x, which means du is equal to 3 times dx. when I calculate my dx, well, dx is equal to du over 3. And now I'm going to do my substitution step. So where the 3x was located, I replaced those with u's. And where the dx is located, I replace that with the du over 3. So this gives me the integral of secant of u times tangent of u times du over 3. Well, the over 3, that becomes a 1/3 outside my integral. So I've got 1/3 times the antiderivative of secant of u times tangent of u du. Well, the antiderivative of secant of u times tangent of u, that's going to give me secant of u. So I get 1/3 times secant of u plus a constant. Well, the last thing here is I'm going to replace u with 3x. So that gives me my answer, which is 1/3 times the secant of 3x plus a constant. All right, example number 6. Find the indefinite integral. So I have the antiderivative of cosecant of 3x, cotangent of 3x, dx. So let's take a look at the solution here. So u is equal to 3x, the stuff that's inside my grouping symbol. Du is equal to 3 times dx. Solving this for dx, that gives me dx is equal to du over 3. So now when I do my substitution, this gives me the integral of cosecant of u times cotangent of u times du over 3. The over 3, that's going to become a 1/3 outside my integral. And I have 1/3 times the integral of cosecant of u cotangent of u du. Well, the antiderivative of cosecant of u cotangent of u, that gives me a negative cosecant of u. So I've got negative 1/3 cosecant of u plus a constant. And then lastly, where the u is located, I'm going to replace that with 3x. So that gives me negative 1/3 times the cosecant of 3x plus a constant. Alright, in the 6 previous examples, we used trigonometric functions. Please notice that a trigonometric function is a container function. That means many times the variable u in the substitution technique will be what's inside the trigonometric function. Well, let's consider this following example. Example number 7. So find the indefinite integral. So this is the indefinite integral of the sine of x over cosine of x dx. Alright, so here my solution, I'm going to let u equal to cosine of x, the thing on the bottom of the fraction. Well, du, when I take the derivative of this equation, this gives me du is equal to, well, the derivative of cosine is a negative sine of x dx. Solving this equation for dx, that gives me dx is equal to negative du over the sine of x. Alright, doing my substitution. So where cosine of x is located, I'm going to replace that with a u. And where the dx is located, I'm going to replace that with a negative du over sine of x. So this is going to give me my negative sign. I decided to put that outside my integral. I've got sine x over u times du over sine of x. And notice my sine of x's, those are going to cancel off. So this gives me the negative of the integral of 1 over u du. The antiderivative of 1 over u is our natural log. So I've got negative the natural log of the absolute value of u plus a constant. And then lastly, where the u is located, I'm going to replace that with a cosine of x. So I get the negative of the natural log of the absolute value of cosine of x plus a constant. Now remember, tangent of x is equal to sine of x over cosine of x. So in this example, example number 7, we just derived the indefinite integral of tangent x. So the antiderivative of tangent x is negative the natural log of the absolute value of cosine of x plus a constant. Well, because of that, the substitution method, that also gives us a few new antiderivative rules. So here are 4 new antiderivative rules that we need to put into our primary memory. So the first one is the antiderivative of tangent of x dx, that is equal to the negative of the natural log of the absolute value of cosine of x plus a constant. Number 2, the antiderivative of cotangent of x dx, that is equal to the natural log of the absolute value of the sine of x plus a constant. The antiderivative of secant of x dx, that is equal to the natural log of the absolute value of secant of x plus tangent of x plus a constant. And then the antiderivative of cosecant of x dx, that's equal to negative natural log of cosecant of x plus cotangent of x plus a constant. Let's take a look at example number 8. So find the indefinite integral, the antiderivative of cotangent of 3x dx. So my solution, I'm going to let u equal to 3x, which means du is 3 times dx, which gives me dx is du over 3. So when I do my u substitution, the 3x becomes a u, and my dx becomes du over 3. And that over 3 is going to become a 1/3 out in front. And then using my antiderivative rule, the new one, the antiderivative of cotangent gives me the natural log of the absolute value of sine. I get 1/3 times the natural log of the absolute value of sine of u plus a constant. And then lastly, I replace u with 3x. So I get 1/3 times the natural log of the absolute value of the sine of the absolute value of the sine of 3x plus a constant. All right, example number 9. Let's find the indefinite integral for the following. So I've got the indefinite integral of the secant of 3x dx. So u is equal to 3x. du is equal to 3 times dx. So I'm going to replace my 3x with u, and I'm going to replace my dx with a du over 3. And then my over 3, that's going to become a 1/3 on the outside. So I get 1/3 times the antiderivative of secant of u times du. And then using that new antiderivative formula, the antiderivative of secant of x is the natural log of secant of x plus tangent of x. So I get 1/3 times the natural log of secant of u plus tangent of u plus a constant. And then lastly, where the u is located, I'm going to replace that with a 3x. All right, example 10. Find the indefinite integral. So I have the antiderivative of 3x times the sine of 5x squared dx. All right, my solution. Well, the first thing, that coefficient, I'm going to bring that coefficient outside my integral. I'm going to let u equal to the stuff that's inside my grouping symbol. So u is equal to 5x squared. Calculating du, well, bringing down my exponent, 2 times 5 gives me a 10, subtracting 1 from my exponent. So I get du is equal to 10x times dx. Solving this equation for dx, I get dx is equal to du over 10 times x. Alright, so using my u substitution, I'm going to replace the 5x squared with u, and I'm going to replace the dx with a du over 10x. So this gives me 3 times the integral of x times the sine of u times du over 10 times x. Well, the over 10, I'm going to bring that outside my integral, so this gives me a 3 over 10 times the integral of, the x's cancel, so that gives me sine of u times du. The antiderivative of sine is a negative cosine, so I get negative 3/10 times the cosine of u plus a constant. And then lastly, I replace u with 5x squared. So I get negative 3/10 times the cosine of 5x squared plus a constant. Now, we have used trigonometric functions for these first 10 examples. Many times, the trigonometric function will have an algebraic expression inside of it, and we need to be prepared to do u substitution when we see trigonometric functions. Now let's take a look at u substitution with some other functions. So example 11. Find the indefinite integral. So I have the integral of e to the negative 3x dx. Here's my solution. U is equal to negative 3x. Du is equal to negative 3 times dx, which gives me dx is equal to negative du over 3. So when I do my u substitution, the negative 3x is going to become a u. The dx is going to be replaced with negative du over 3. And that negative, I'm going to put that on the outside of my over 3, is a 1/3. So this gives me the negative 1/3 times the antiderivative of e to the u times du. The antiderivative of e to the u is e to the u. So I get negative 1/3 e to the u plus a constant. And then lastly, I replace u with negative 3x. So I get negative 1/3 e to the negative 3x plus a constant. All right, let's take a look at example 12. Find the indefinite integral. So I have the integral of 5x times e to the 3x squared dx. Now let's take a look at the solution. Again, I'm going to take that coefficient of 5 and put that outside my integral. So I've got 5 times the integral of x times e to the 3x squared dx. I'm going to let u equal to 3x squared, the stuff in the exponent. So u is equal to 3x squared, which gives me du is equal to 6x times dx. Solving this equation for dx, that gives me dx is equal to du over 6. So doing my u substitution, where the 3x squared is at, I replace that with a u. Where the dx is at, I'm going to replace that with a du over 6x. So I get 5 times the integral of x times e to the u times du over 6x. The over 6, I'm going to bring that out in front, so it gives me 5 over 6 times the antiderivative. The x's cancel, so that leaves me with just e to the u times du. The antiderivative of e to the u is e to the u, so I get 5/6 e to the u plus a constant. And then lastly, I'm going to replace u with 3x squared. So my answer is going to be 5 over 6 times e, and that should be a 3x squared, not a 5x squared. So that should be 3x squared plus c. For our exponential functions, u will end up being the algebraic expression inside the exponent. All right, number 13, find the indefinite integral. So I have the integral of 3x over x squared plus 4 dx. So my solution, u is equal to x squared plus 4. So u is equal to the bottom of this fraction. Du is going to be 2x dx, and that gives me dx is equal to du over 2x. So, applying my u substitution, where the x squared plus 4 was at, I replaced that with the u, and I replaced my dx with du over 2x. Alright, so the coefficient of 3 and the coefficient of over 2, that's going to come out in front, so I get 3 halves times. The x's cancel, so I get 1 over u du. The antiderivative of 1 over u is the natural log of the absolute value of u. So I have 3 halves times the natural log of the absolute value of u plus a constant. And now I'm going to replace u with x squared plus 4. So I have 3 halves times the natural log of the absolute value of x squared plus 4 plus a constant. So any questions on it? Alright, so looking at example 7 and example 13. So 13 was this one. Notice the x squared plus 4 is on the bottom. And if I go up to 7, 7 was the one where we had a cosine on the bottom. So whenever we have fractions, so looking at examples 7 and 13, whenever we have fractions, a lot of times we're going to let u equal to the denominator of the fraction. And that sometimes will work for our u substitution. Now let's take a look at example 14. So find the indefinite integral for the following. So I've got the integral of 3x times the square root of x squared plus 4 dx. So my solution, I'm going to let u equal to x squared plus 4, the stuff inside my square root. So du is going to be 2 times x dx. And that means dx is going to be du over 2x. So applying my substitution, the x squared plus 4 gets replaced with the u, and the dx gets replaced with du over 2x. So I have the integral of 3 times x times the square root of u times du over 2x. My x's are going to cancel, and I'm going to get a 3 halves times the integral of the square root of u, that becomes a u to the 1/2 du. Taking my antiderivative, I add 1 to the exponent, divide by the new exponent. So 1/2 plus 1 gives me a 3 halves, and dividing by 3 halves is the same thing as multiplying by the reciprocal, multiplying by 2/3. So I get 3 halves times 2/3 times u to the 3 halves exponent plus c. And then lastly, I'm going to replace my u with x squared plus 4. So I've got x squared plus 4 raised to the 3 halves exponent plus a constant. Alright, let's take a look at number 15. Find the indefinite integral for the following. So I have the integral of 3x times x squared plus 4, all in parentheses, raised to the 5th power dx. Alright, so I'm going to let u equal to the x squared plus 4. That was the algebraic expression inside my grouping symbol. Du is going to equal 2x dx, which gives me dx is equal to du over 2x. So doing my substitution, this is going to give me the antiderivative of 3x times u to the 5th power times a du over 2x. My x's are going to reduce, and that's going to leave me with a 3 halves times the integral of u to the 5th power times du. taking the antiderivative of this, adding 1 to the exponent, dividing by the new exponent. So I get 3/2 times 1/6 u to the 6th power plus c. My 2/3 times my 1/6, that's going to become a 1/4, times x squared plus 4 raised to the 6th power plus a constant. So these two previous examples show U substitution method working with grouping symbols such as parentheses and square roots. So again, if you see any grouping symbol, parentheses, square roots, exponentials, trig functions, many times we're going to let U equal to the stuff that's inside the grouping symbol. Alright, let's take a look at example 16. So find the indefinite integral for the following. So I have the integral of x times the square root of x minus 3 dx. Alright, so my solution. U is equal to x minus 3. du is equal to dx. So when I do my u substitution, this gives me the integral of x times the square root of u times du. Now notice in this example, the variable outside the grouping symbol, this x, did not reduce. So for this one, we're going to have to go back up to our original u substitution formula. U is equal to x minus 3, and we're going to have to solve this for x. So if I add 3 to both sides, that gives me u plus 3 is equal to x, or x is equal to u plus 3. So if there are some variables that are left over that we can't reduce, we've got to go back to our original formula, and we got to solve it for x. And now what we're going to do is we're going to replace this x with u plus 3. So that remaining x is going to get replaced with a u plus 3. So this gives me the integral of u plus 3 times the square root of u du. Alright, simplifying this a bit, well, square root of u is a u to the 1/2. Distribute my u to the 1/2 through. So u to the first power times a u to the 1/2 power. Exponent of 1 plus an exponent of 1/2 gives me an exponent of 3/2, plus 3 times u to the 1/2 du. Taking the antiderivative, adding 1 to the exponent, dividing by the new exponent. So 3/2 plus 1 gives me a 5/2, and then dividing by 5/2, that gives me the same thing as multiplying by 2/5. So 2/5 u to the 5/2 plus 3 times, well, add 1 to the exponent, that gives me a 3/2. Divide by 3/2, which is the same as multiplying by the reciprocal, so 3 times 2/3, u to the 3/2 plus a constant. And then lastly, we're going to replace all of our u's with x minus 3's. So I have 2/5 times x minus 3 to the 5/2 exponent plus 2 times x minus 3 to the 3/2 exponent plus a constant. Alright, example number 17. So find the indefinite integral for the following. So I have the antiderivative of tangent of x times secant squared of x dx. Alright, my solution here. I'm going to let u equal to the tangent of x. When I take the derivative of tangent, du is equal to secant squared of x dx. And if I solve this for dx, this gives me dx is equal to du over secant squared of x. Performing my u substitution, this gives me the antiderivative of u times secant squared of x times du over secant squared of x. And my secant squareds cancel off. And I'm left with the antiderivative of u du. Taking my antiderivative, add 1 to the exponent, divide by the new exponent. So that ends up giving me 1/2 u squared plus a constant. And then lastly, I'm going to replace u with tangent. So I get 1/2 tangent squared of x plus a constant. Now notice with this example, if we take the derivative of the answer, the 1/2 tangent squared x plus a constant, we have to use the chain rule. U substitution is the reverse of our chain rule. So problems where I had to use the chain rule to take the derivative, U substitution many times is used to take the antiderivative of that result. Also notice that this does not fit that template where I say let U equal to the algebra inside of grouping. So it doesn't match any of those patterns. This example also emphasizes why we need to have all the derivative and all the antiderivative properties not just memorized, but known as well as how to just add regular numbers. Because if you don't notice that the derivative tangent is secant squared, then it's going to be difficult to be able to see the U substitution. All right, number 18. Find the definite integral. So here we have the integral from 3 to 7 of the square root of x minus 3 dx. All right, my solution. I've got u is equal to x minus 3, du is equal to dx. Now notice what happens in the substitution here. I get the integral from 3 to 7 of the square root of u times du. Now, if we take a look at this integral and we don't see what the original problem is, in other words, if somebody was to come into this video right now and they see only this line here, the integral from 3 to 7 of the square root of u, then they won't know that this came from substitution. And that person will think that when we find the antiderivative of u, we're going to plug 3 and 7 into that equation that we get for u. This is not correct. So what's going to happen here is whenever we change our variables from x's to u's, we also have to change these endpoints. So let's take a look at how to change the endpoints. So the original endpoints were 3 to 7. So change x values to u values. When x is equal to 3, well, u, my original u was x minus 3. So when x is equal to 3, u equal to x minus 3 becomes u is equal to 3 minus 3, so u is equal to 0. When x is 3, u is going to be 0. The other endpoint was a 7. So when x is equal to 7, u equal to x minus 3 becomes u is equal to 7 minus 3, which gives me u is equal to 4. So this integral, instead of saying 3 to 7, that should have said the integral from 0 to 4 of the square root of u times du. Now if somebody walks in and sees this, then they know what to do. Well, changing my square root to a 1/2 exponent, so I have the integral from 0 to 4 of u to the 1/2 du. Add 1 to the exponent, divide by the new exponent, so that gives me u to the 3/2, and with a coefficient of 2/3, again, flipping the coefficient, changing to multiplication, and this is evaluated from 0 to 4. All right, u to the 3/2, that's the same thing as the square root of u to the 3rd power. So plugging in my endpoints, I get 2/3 times the square root of 4 cubed minus 2/3 times the square root of 0 cubed. Well, the 0 stuff, that's going to go away. Square root of 4 is 2. 2 to the 3rd power is 8, and 8 times 2 is 16. So my answer is 16 over 3. Thank you for watching this video, and I hope to see you next time.